A couple of weeks ago, when we were working on dot product, I mentioned that there are two forms of vector multiplication, one of which being the dot product that we used for finding the angle between vectors. We use that a lot with unit vectors. Now we're going to talk about the other form of vector multiplication, the cross product. So if you remember, we said the dot product was this A dot B. This cross product is much like the dot product was A with a dot in the middle, B. It's going to be A cross with the little x, kind of like a multiplication sign. The cross product is going to be A cross B. That's how we define our cross product. It is a vector. Unlike the dot product, which always gave us a scalar answer, the cross product always gives us an answer that is a vector. We often see the equation written as the magnitude of A times the magnitude of B times sine of theta, where dot product used cosine theta, sine theta times the unit vector, right? Because cross product is always a vector. And where this cross product comes from is from a matrix. So the way that we get cross product is from a matrix with I, J, and K, where you have AX, AY, AZ, BX, BY, and BZ, and you solve the matrix and it gives you a vector answer, right? So this is where the cross product is coming from. It's coming from this matrix math, which we'll go through here in a second. Just one more major thing I want to mention about how the cross product is different from the dot product is that it's not communicative, right? So what I mean by that is that A cross B does not equal B cross A. Actually, A cross B equals negative B cross A. Right, so just note that because it is a vector, because it has a direction associated with it, that it is not communicative. It matters which one you're multiplying by which. And the reason we care about this cross product at all is because we're going to use it in our moments. So the moment is the force vector crossed with the position vector r. So before we had seen the distance d, the perpendicular distance d, now we're saying anywhere in space that I have some kind of vector, I can find any vector r. It doesn't have to be perpendicular. I can find the vector r, and I can do the cross product of f crossed with r to find my moment vector. But before we do an example using the cross product, let's talk about this cross product matrix, which you might have come across matrices in some of your earlier math classes, or if you're taking some advanced math classes, linear algebra, matrices tend to come up a lot more. But if you're not familiar, this is how we go about solving this matrix, right? So our matrix here, if we have A cross B, in our 3D system, we end up with this 3x3 matrix. And you may see it written with this bracket format, or you may see it written with just the straight lines on the sides. AX, AY, AZ. Either way is acceptable. It's just a small notational difference. And the way we go about solving this 3x3 matrix is basically by breaking it down into 3 smaller matrices. So what we'll do is we take the I hat and then we create a smaller 2x2 matrix that we can solve with the rows that are not under I hat. So we're going to do that for each one. We do I hat, then the 2 rows that are not under I hat. J hat, the 2 rows that are not under J hat, and K hat, the 2 rows that are not under K hat. So what that looks like is my I hat term is going to be I, and then times the matrix of AY, AZ, BY, BZ. And this is really important. This is something a lot of people forget. When we do the middle term J hat, and we take these two rows, we have to subtract. It is always subtracted. Minus J hat, AX, AZ, BX, BZ. And then our K hat goes back to normal, right? It's just going to be the plus K hat, matrix of AX, AY, BX, BY. And the way we do a matrix is we multiply across and then subtract the multiplication across. Right, so we can see kind of where this cross product comes from. It comes from the crosses of these matrices, right? So in this case, I hat times AY BZ minus AZ BY minus the J hat gets a minus because remember, it's in a bigger matrix, right? We subtract off the second term when we do this cross here, right? So this is minus J hat, whoops, sorry, not the matrix. I don't want the matrix symbol, just parenthesis. AX times BZ minus AZ times BX. And then our K hat terms plus K hat, multiply across down, AX BY minus AY times BX. And this is the full written out form. This is the full A cross B vector gives you this resultant. This is how we solve that 3x3 matrix. And again, that's going to be important when we're doing this moment analysis. When we do the vector moment analysis, we do it using this cross product formula. So let's take a look at an example where we'll go over how we would do a scalar analysis and how we would do a vector analysis, both for the same problem. So let's take a look at this example. We want to find the moment about point O, just this point over here, given this force of 400 newtons that's acting 0.4 meters over and 0.2 meters down at a 30-degree angle. We want to find the moment of this force about point O. So there are a couple of ways we could do that. One is we can think about our scalar analysis, and that was our M equals FD. But this may not be our best approach because we have to find what that D value is, right? Because if I look at my line of action of my force here, this is my line of action, and I need to find the perpendicular distance to this line. So I'm looking for this distance right here, right? And how do I solve that? How do I find that? I can, but it's going to be a lot of complicated geometry when I could have just used scalar analysis by components, the fx and fy, dx and dy, or I could have used vector analysis, which are going to be easier and are going to save me some time. So I'm actually not going to try to find D in this scenario. It's going to be a little bit complicated. So I'm just going to do scalar by components and then show the vector analysis. So the scalar by components is what we did in the last video. And get rid of these there. My scalar by components is going to be that M about 0.0 fx dy plus fy dx. And I can see this is going to be fairly reasonable to try to solve, right? So if I think of my fx times dy, my fx is this 400 newtons times cosine of 30, 400 cosine 30 times dy, the y distance to this point where f starts. So that's this 0.2. 0.2. But we need to check, is this positive or negative? Right, so the x component of my force here goes towards the right, right? So if I do my right-hand rule and I think about the direction that the moment is going in, is it clockwise or counterclockwise? About the moment here, whoop, it is counterclockwise. And I'm going to assume counterclockwise is positive, so I'm going to leave this as a positive. And then let's look at my y component. So my y component I have here, down, it is 400 sine 30, right? That's the y component of that force, times the x distance, which is that 0.4 meters. So now, is this positive or negative? Let's check with our right-hand rule. Check, is it going counterclockwise or clockwise about point O? It's going clockwise. It's actually going the opposite direction, right? So that means this has to be a negative term. We have to subtract this because they're going, the x component and the y component are going in opposite directions. Now we can think about, what should the overall direction be? If we think about f and do the moment for the whole of f itself, it should give us a clockwise moment. So we should expect to get a negative number here. We should expect to see a clockwise moment if we do the right-hand rule for the overall f. So in this case, when I punch this into my calculator, I get moment about O is negative 98.6 Newton meters. And again, I have to explain what that means. I have to determine what that means. I have to give the direction. So here I can say negative 98 Newton meters counterclockwise. Or if I want it to be positive, I can say 98.6 Newton meters clockwise. Right? These two answers are the exact same thing. It's just how you want to write the notation. Either way is 100% okay. So now let's do this example as a vector analysis. So we know our moment is going to be the cross product of the force vector times the position vector. And the position vector is just the distance from the point we're interested in to F. Right? So R is this vector here. This is the vector R. If I were to write that out, R is going to be, I can put it in Cartesian form even. I already have my distances. So I can say 0.4 I hat minus 0.2 j hat. Now when I write these F and R vectors, I do want to keep the sign convention. I do want to keep the x and y, positive x and y axes, these sign conventions for positive and negative, because they're going to affect the direction of our moment. So my R, my x is in the positive x direction, but my y is in the negative y direction. And the same with my force. When I'm setting up these vectors, it's just like we were doing weeks ago, right? Setting up the force vectors and the position vectors, you do want the signs, the correct signs. So my force vector here is going to be 400 sine 30 I hat minus 400 cosine 30 j hat. And those are my two vectors. And so I'm going to go ahead and do the cross product to find what my moment is. So my moment is going to be the cross product I, j, k of 0.4, negative 0.2, and 0, right? There's no z component in these. And then, let's see, 400 sine 30 is 200, and 400 cosine 30 going to give me negative 346.4. And then again, no z component. I should have lined up my, whoops, I'm sorry, microphone. I should have lined up my columns a little bit better here, but it's okay. It's going to work out either way. The important thing that I want to note here is that these zeros are going to get a lot of my terms to actually cancel out. So when I go and do this I hat matrix, I'm going to have negative 0.2, negative 0.2, 0, negative 346.4, 0. And if I do the multiplication on that, I'm getting negative 0.2 times 0, that's 0, minus negative 346 times 0, again, is 0. So this whole I term cancels out to 0. Same with the j hat term, right? Because I've got that 0.40, 200, 0. Multiplying by zeros, I get the whole term going to 0. So the only term I'm going to be left with in this case, because I am working in 2D, is going to be a k hat term. And that kind of makes sense with our right-hand rule, right? Our thumb is pointing along the moment axis, and that's usually out of the page at us, right? That moment axis is the z-axis when we're working in these 2D problems. So you're only going to end up with a k hat component. So let me make some room here. I'm going to get rid of this. And I'm just going to put the k hat term in here. Right, so my moment actually equals 0.4 times negative 346.4 minus negative 0.2 times 200. And that is in the k hat direction. So when I punch all of that in, I find I do get the same answer that we got from scalar analysis, right? A moment of negative 98.6. Now I just have the k hat direction, right? So I know from the k hat direction, that's the positive moment axis. If I point my thumb in the direction of the moment axis, k hat direction, I'm going to find it's going counterclockwise. So it's negative 896. It's pointing actually in the negative z direction, right? So that tells me if I were to write my moment, I could write it like this. Or again, I can write moment is a positive 98.6 k hat clockwise. And I'm just going to put CW. Yeah. Again, you only need to write one of these answers. Just whichever one makes the most sense to you notationally, if you want to keep everything in the positive, or if you just want to always know your notation, right? Know that you're going clockwise or counterclockwise, what your positives and negatives mean. That's what's important. Let's look at one last example. Here we've got this pipe with a force coming off of it of 120 pounds that follows along this brown rope that's connected to the wall at point C. So the blue thing is some pipe we have sticking out of the wall, and then there's a rope connecting the end of the pipe at point B to the wall at point C. So we want to determine the moment about point O, and we know our moment equation is R cross F. So as you can see in this one, we're not given R and we're not given F. We're going to have to find both of those vectors. So our R vector is pretty straightforward to find, right? It's from the origin up to where F begins, right? So this is our R vector. It goes from the origin to this point B. So our position vector for R is just going to be the location of point B, right? Because you're subtracting the origin, which is 0, 0, 0. So your R vector, going to be point B is 1 foot in the X direction. It is 4 feet in the positive Y direction, and then 2 feet in the positive Z direction. So this is our R vector that we're going to be plugging in right here. But we'll also need to find our F vector. And we're going to have to use the same process that we used a couple weeks ago, where we had a force along a line and we weren't given it in Cartesian form. We had to turn it into Cartesian form by creating a position vector, turning the position vector into a unit vector, and then multiplying by the force, right? So this is revisiting that concept that we have this force and we need to turn it into Cartesian form basically so that we can do the cross product. Right, so let's write, so this is our R in the equation, but our R for the force vector, I'm going to call it RBC, right? It's going from point B to point C. So our point B, we already said, is at 1, 4, 2, and point C is on the x-axis, so it has no y or z components. It's going to only have an x component, right? So it's that C is going to be 5 feet in the x direction minus 1, and then no value for x or y. So it's going to be 0, minus 4, and 0, minus 2. So this is our position vector for BC, representing the line that the force is acting along. The line of action of the force can be represented by this position vector 4, -4, -2. And to turn that into a unit vector, all we do is divide by the magnitude. Right, that 4 squared plus 4 squared plus 2 squared gives us the unit vector. So when I multiply all of that out and I plug that into my calculator, right, I divide my magnitude by each term, I'm going to get that my unit vector is, this bottom term works out to 6. So it's going to be 4/6, -4/6, and -2/6. That'll be my unit vector. Then I multiply my unit vector by the magnitude of my force, and that's how I get the force vector. So I multiply this guy by 120 pounds, and that's going to give me my force vector that we're going to use. So my force vector, 120 times 4/6 gives me 80 I hat, minus 120 times -4/6 gives me -80 j hat. And then 120 times -2/6 is -40 k hat. Right, so now I have my two vectors. All I need to do is plug them into my matrix, right? Do my cross product. Make some room here. We'll write out our cross product. Our moment is I, j, k. Then our R vector is 1, 4, 2. And our force vector is 80, -80, -40. So we go through and do this cross product. We get the I hat term times this matrix, right? So that's going to be 4 times -40 minus 2 times -80 minus our j hat term, right? Always minus j hat. Our 1 times -40 1 times negative 40 minus 2 times 80. 2 times 80, our j hat term, and then finally our k hat term, right? This matrix to the left over here, plus k hat of 1 times negative 80 minus 4 times 80. And that's our full equation. When we plug each term into the calculator, end up with our moment of 200 I hat minus 400 k hat pound feet. Sorry, this is j hat. Sorry. There is no I hat term if we notice 4 times negative 40 minus 2 times negative 80, right? This is negative 160 plus 160. So our I hat term just goes away. We don't even need to write our I hat term. This is 200 j hat. 200 j hat minus 400 k hat pound feet. That is our moment.